All right, Precalc AB students, this is Mr. Morris here, and this is 2.3 day 2 notes. We're going to sketch a possible graph for the function f of x such that the following wonderful conditions are met. So f of negative 3 has to exist. The limit of f of x as x approaches negative 3 from the left has to equal f of negative 3, and the limit of f of x as x approaches negative 3 from the right does not equal f of negative 3. I said possible here because there's a variety of ways you can graph this. So we will not provide you answers on your homework necessarily because there are different ways that you can graph these. All right. So f of x, make sure you label like I have here. I have the axes set up here, and I've already put tick marks, which you have to have over to x equals negative 3, so we can see you're precisely at the right x value. For f of negative 3 to exist, I'm just going to put a y value. Now, it doesn't specify what y value, so that's where your graph could vary. That could be in the positive. You could have a negative y value. I just chose to put it right there. The limit of f of x as x approaches negative 3 from the left has to equal that same y value for f of negative 3. So as I approach this graph from the left, I'm actually going to draw this something like that. And I'll just stop there. And so that makes those conditions true. All right. Now, the second part, the limit of f of x as x approaches negative 3 from the right will not equal f of negative 3. So I need this graph to have some discontinuity at x equals negative 3. All right. And so I'm going to put an open dot here at x equals negative 3. And to the right, I'm just going to graph this going like this, something like that. All right. And you know that I could have meant for that to be perfectly horizontal, or it can curve as long as I have a function. Make sure we're particular about that. It passes all definitions of a function, the vertical line test for a graph. All right, now let's go back and make sure we've met all of our conditions. If we have, then this is correct. F of negative 3 exists. Yes, f of negative 3 is right there. Solid. All right. Limit of f of x as x approaches negative 3 from the left equals that f of negative 3. So as I approach from the left, yes, I get that f of negative 3 y value. The limit of f of x as x approaches negative 3 from the right does not equal that f of negative 3, and it does not. There's an open dot here, and it's certainly not that same y value. So I know I have this correct. All right, let's move on to example 2. All right, so in this case, I have the conditions that I need to meet here is the limit of f of x as x approaches 2 from the left exists. The limit of f of x as x approaches 2 from the right also exists. All right. But the limit of f of x as x approaches 2 does not equal the y value for f of 2. All right. So again, I set this up. I have f of x labeled. I have, in this case, we went at x equals positive 2. So I have 2 marks here. Our y values here particularly don't matter, just as they did not in number 1. And so this is a classic problem where we have a hole in our graph. The limit from the left and the limit from the right as x approaches 2 does exist. So I've got something like this. Now I chose to make that linear. You could have this piece on the left curve and this piece on the right curve, just as long as it's a function. And so clearly this first part I've met. All right, now how about the second part? The limit of f of x, well, actually, I guess it's the third part, but the limit of f of x as x approaches 2 does not equal f of 2. Well, currently f of 2 is undefined. And so I have met the conditions of this. Now I'm going to make it even more perfect, if that's possible. I'm going to put a solid dot here. This part's actually not necessary, but I'm really making sure this part here is true. Even though before, without that solid dot, f of 2 was not equal to the limit because f of 2 is simply not defined, I just put this here to define f of 2 specifically somewhere else. And so now all 3 conditions are met. The limit of f of x as x approaches 2 from the left exists. It's this y value of the whole. The limit of f of x as x approaches 2 from the right exists. From the right, it's the y value of this hole. Remember, a limit can exist at a hole, but the limit of f of x as x approaches 2 is not equal to this y value, right? The limit is not f of 2. All right. Okay, so that problem is complete. All right, so this next example says find the value or values, because there could be more than one, or there could be one, of k so that the below function f of x is a continuous function. All right, piecewise functions are more complicated. All right, they're more complicated to do domain and range. They're more complicated to graph. And in this case, and in most cases, limits are more complicated for these. So let's analyze this piece by piece. And so this right here, let's say I have k squared minus x squared when x is less than 2. So I've given you a possible graph of that over here, right? So over here on this graph right here, this, no matter what k is, and in this particular case, I just graphed it sort of generically, but it would be a parabola that opens down. And so at x is less than 2, it would look something like that. All right. And the key here is to look at this as far as the continuity standpoint. We really have three things to look at. First of all, this function itself, k squared minus x squared. Let's assume we knew what k is. It'd just be some number. That parabola is a polynomial, so it would be continuous everywhere. All right. How about this part right here? Now, I'll sketch this down here over to the right here in a second. But if we knew what k is, this would be a particular line, equation of a line if we were to graph it, all right, which again is a polynomial and would be continuous everywhere. So the issue then becomes, well, where am I worried about continuity on this particular piecewise function? Well, all of it has to do with this value right here. So where x is 2. So over here on this graph, I have 2 here. All right, so I have this at x equals 2. And I've graphed a possible way that the upper piece or the parabola would look like. Now, let's talk about a couple scenarios if the line were graphed. So this part has the equal to part, that x is greater than or equal to 2. And so let's assume that it graphed here. And it went from here like that. All right, and that's the line. Well, in this case, it would not be continuous because there is a gap here between the y values of the two different pieces. All right, so clearly, if the y value for the parabola and the line, these two different pieces, are different, then it's not continuous there. All right, so let's erase that. And let's say, though, for instance, that when I graph the line, the y value where x is 2 ends up being here. Well, now notice an open dot and then a solid dot fills in. And if I graphed it something like that, now indeed they would be continuous, or this piecewise function overall would be continuous at x equals 2. So this is really the spot we're concerned about. All right. And the key here is this point right here. When I plug in a value to this left piece, this graph, I need to get the same y value as when I plug into this right piece, which would occur at this place where they would either connect or not connect. All right, so that's the key to the algebra here, right? So I've worked this all out so I can just talk through it real quick. All right, so let me scroll this a little bit. I think I have this a little too low here. All right, and so a second ago I did say that this graph is continuous at x equals 2 because that's really the spot we're really concerned about, but the graph is continuous everywhere, all right? In particular, the issue we were worried about is at x equals 2. All right, so let's look at the algebra behind this. And I've highlighted this already. And so what is happening here is because we want these y values to be the same, I'm going to set each piece equal to each other. So when x is 2, I'm going to be able to calculate the k value that will result in this graph coming together here at this same point to have the same y value. All right? And so k squared minus x squared will equal 1.5kx, which I talked a lot about the theory or the graph behind this, but ultimately, in this case, it didn't say to graph it. I just showed you that for demonstration purposes. All we really have to do is go to here and say k squared minus x squared equals 1.5kx when x is 2. All right, now we'll plug in 2 for x. Be careful, all right? We are plugging in for x, not for k. We're looking for k. So 2 goes in for x squared, and then 2 goes in for x here. Then I just started simplifying. So let me scroll this up a little more. All right, so 2 squared is 4. 2 times 1.5 is 3. So you get k squared minus 4 equals 3k. Then in the next step, it's just moving everything on one side equal to 0 because I have a quadratic. So I subtracted 3k from both sides. So k squared minus 3k minus 4 equals 0. Do not forget to write this 0 here. A lot of students tend to get really sloppy with notation and leave these zeros off. All right, do not do that. All right, this next step from here down, you can choose to use a quadratic formula or factor it. All right, and so this factors nicely numbers that multiply to -4 and add to -3. There's a 1 in front of the k squared, so it makes it for an easier factoring problem. So those numbers are -4 and +1. Always check your factoring real quick to make sure it's correct, but this is indeed correct. Then I'm using zero product property. Again, it's important to have this 0 written over here. When k minus 4 is equal to 0, k must be 4. When k plus 1 is equal to 0, k has to be equal to -1. And so there are two possibilities for k, which means there are really two complete sets of piecewise functions that would make this a continuous function at x equals 2 or entirely continuous on its entire domain. All right, that concludes this lesson. Have a great day.